So let's talk about something called alternating series. These are super useful and we can do a lot with them. So an alternating series is one whose terms are alternatively positive and negative on consecutive terms, right? It just means that the terms go positive, negative forever, or opposite, negative, positive, negative, positive. There's an example of one on the middle of your screen, right? So something like negative 1 to the n plus 1 power over n, right? If I just plug in n of 1, 2, 3, etc., I end up with the terms 1 minus 1/2 plus 1/3 minus 1/4, right, out to infinity. So we can recognize an alternating series if it has an alternator. So some different alternators that you might see inside of a series are like negative 1 to the n, or negative 1 to the n plus 1, or n minus 1 power, right? The difference in the exponents is just changing whether or not you're going positive, negative, or negative, positive. Some of the sneakier alternators that you might see are using your trig functions. So like cosine of n pi, or pi n, however you want to say it, right? Because if I have 1 pi, cosine of pi is negative 1, and then cosine of 2 pi is positive 1, 3 pi is back to negative 1, right? So it's going negative 1, positive 1, negative 1, positive 1. Or this one is less frequent that you'll see. The cosine one pops up a lot more, but this one will pop up sometimes, right? So sine is positive and negative 1 at the pi over 2 marks, and you only want the odd pi over 2s, right? 1 pi over 2, 3 pi over 2, 5 pi over 2. So in order to get that odd number out, you need to use 2n minus 1, so you're always getting an odd number times pi. So that way you're never going like pi over 2, pi, 3 pi over 2, 2 pi, right? You're only hitting the pi over 2 marks. So in general, and if we're looking at just a general infinite series, knowing that the limit of the sequence goes to 0, it tells us very little about the convergence, except that it's a possibility that it could converge, but it doesn't tell us it does. But for an alternating series, it actually helps us out a ton. So to prove convergence for alternating series, we have something called the alternating series test. This only works for alternating series, right? Duh, it's in the name, right? And what it says is if you have a sequence that's greater than 0, meaning you have a positive sequence on the inside, so your alternating series, which could look like either one of those terms, right? You have an alternator, right, times a sequence, basically, right? Your alternating series is going to converge if both of these following conditions are met. The first thing is that the limit as n goes to infinity of the sequence equals 0. So note that this is, right, the sequence without the alternator. Right, you can also consider it as like the absolute value of it, right? Just get rid of the alternator, take the limit. If it equals 0, great. The next thing that you want to do is the sequence without the alternator, again, right? Just the sequence an is decreasing or non-increasing, meaning that it's staying constant and then going down, right? That is that the nth plus 1 term is less than or equal to the nth term, right? So each consecutive term is equal to or smaller than the previous term. So something super important to take note of is that for alternating series test, you can only use it for convergence. You cannot say the series diverges by the alternating series test. If you say that, the problem is automatically wrong across the board. But the cool thing about alternating series is that if you use the alternating series test and you're like, this doesn't converge, I'm fairly certain it diverges, you can usually just say that it's going to diverge by the nth term test. Right, so those are really the two options there. So let's do a couple of quick examples to show how to use this. So we're going to determine if these converge or diverge. And and that was leftover directions from another lesson that I just copy and pasted. My bad. Okay. So in our first series, we can see that we have cosine of pi n, right? There's our alternator. Right, you can also think of that as being equal to, right, negative 1 to the nth power, because you're going negative 1, positive 1, negative 1, positive 1, right? And that's all over n. Right, so we have an alternating series. So the first thing I'm going to do is test the limit as n goes to infinity of 1 over n. Okay, that is in fact equal to 0. So first condition is satisfied. And then the next thing we need to do is we need to show that 1 over n plus 1 is less than or equal to 1 over n. So all I did was I took my n and I plugged in n plus 1. So you want to show that the nth plus 1 term is less than or equal to the nth term, meaning that the next term is less than or equal to the previous term. So I'm going to go ahead and solve this by cross multiplying. So n less than or equal to n plus 1, right? That means that 0 is less than or equal to 1. Okay, that's true. So this is a true inequality for all n greater than or equal to 1, meaning that it's decreasing for all values of n that you're going to plug in. So because it meets both of those requirements, we can say, therefore, this converges by the alternating series test. Right, that's all you have to do. So let's apply that to another scenario. So in our second scenario, it looks a little bit more intense, right? So we have our alternator here, right? -1 to the n plus 1 times n over 2n plus 1. So the first thing we're going to do is we're going to test the limit as n goes to infinity of n over 2n plus 1. So that equals 1/2, and that is not equal to 0. So we can't use this to prove convergence with the alternating series test. So instead, right, let's look at, okay, what's the limit as n goes to infinity of the whole thing? Right? So the limit we know of this part, right, I can split this up using my limit properties. Right, -1 to the n plus 1, right, times the limit as n goes to infinity, right? So it's equal to, right, the limit as n goes to infinity, actually I'm not even gonna write that out, right? So the limit of the first part, right, -1 to n plus 1, right, that's oscillating, that doesn't exist. And then we know that the limit of the other part is 1/2, we just did that, right? So the overall limit does not exist, which means that this, right, this diverges by the nth term test. Right, remember nth term test proves divergence if the limit is not equal to 0 or if it doesn't exist. Right, so typically you're going to use the nth term test when you think it diverges instead of converges by alternating series test. So there's a little bit more nuance to alternating series than there are to others. So typically with most series, we just say it converges or it diverges. But alternating series has kind of more nuance to the type of convergence it has. So alternating series converge in two different ways. They can converge absolutely or conditionally. And so it basically depends on if the series converges with or without an alternator. So we say a series converges absolutely if the alternating series and the non-alternating series both converge, right? So it means that it converges, right, both with and without an alternator. A series converges conditionally, however, if the alternating series converges, right, our alternating series converges, but the normal series without the alternator does not converge. So it converges conditionally if, right, only the alternating series converges. So let's go through some examples of how to do that. Okay, so let's look at these two series. So we're going to prove convergence. They both converge, but we're going to show that they converge with the alternating series test, and then we're going to test for absolute and conditional convergence. Right, so the first thing I'm going to do is I'm going to say, okay, what's the limit as n goes to infinity of the non-alternating series? So 1 over n minus 5 squared plus 1. Okay, well, that's obviously going to 0, so that part works. And then I want to show that 1 over n plus 1 minus 5, right? Just plugging in n plus 1 for my n here. Squared plus 1 is less than or equal to 1 over n minus 5 squared plus 1. Okay, so if I cross multiply, I'm going to end up with this. So I'm going to get n minus 4 squared plus 1. Right, so my 1's are going to cancel out, and if I square these things, I'm going to get n squared minus 10n plus 25 less than or equal to n squared minus 8n plus 16. Okay, so my n squareds will cancel out, Okay, let's see. If I subtract 16, I get 9 is less than or equal. Add 10n over, I get 2n. So 4.5 is less than or equal to n. So what that tells us is that this is a true inequality, right? The nth plus 1 term is less than or equal to the nth term, right, for n greater than or equal to 5. And that's fine. As long as it eventually comes down to all decreasing, it's totally fine if the first few terms are not decreasing. As long as it is eventually decreasing, you're good. Okay, so that means that this is true, right? Our two conditions are met, right? So this is going to converge by the alternating series test. So now we need to see if this is going to be absolute or conditional. So we're going to test that by saying, okay, let's look at the same series but without the alternator. Okay, so we know that the nth term test is not going to work here, right? Because we already took the limit of this and it equaled 0. So I'm going to compare this to the series from 1 to infinity of just 1 over n squared, right? If I take out that extra stuff in the denominator, it's essentially 1 over n squared. Now, you could try and use the direct comparison test. That might work here. I'm a much bigger fan of limit comparison because I don't like having to prove that inequality statement for the direct comparison test. So if I do the limit comparison of the sequence I'm trying to figure out over the sequence I already know about, right? That's going to be the limit as n goes to infinity of n squared over n minus 5 squared, all plus 1. So that limit is equal to 1, which is positive and finite. So this is going to converge by limit comparison. So because both the alternating version and the non-alternating version, they both converge, we're going to say that this converges absolutely. Right? It absolutely converges no matter what, right? Whether there is alternator or not. So now if we look at our other series here, right, we have negative 1 to the n plus 1 over n, series from 1 to infinity. Right, so if I quick test it with the alternating series test, right, I take out the alternator, right, the limit of that is just 0. And now I want to show is 1 over n plus 1 less than or equal to 1 over n. Well, we already did this, right? If we scroll back up, right, we already proved that that's going to be a true statement for all n greater than or equal to 1, so I'm just going to not do the work again. Right, that's true for n greater than or equal to 1. So we can say this converges by the alternating series test. Right, so now we're going to look at the non-alternating version. So the sum from 1 to infinity of just 1 over n. So that's a p-series, right? That is the harmonic series, in fact. It's the very famous, very useful series, and we know that the harmonic series is divergent, right? So that since this diverges, right, you can say it diverges by the harmonic series, since it's the harmonic series, or you can say diverges by the p-series test, right? So because the alternating series converges, but the non-alternating series diverges, we're going to say that this one converges conditionally. It converges on the condition that there's an alternator there. So as if the two different types of convergence wasn't enough nuance for alternating series, there's actually more nuance in the fact that we can actually figure out an error amount. So we can't actually figure out the exact value of a convergent alternating series like we can with a geometric series or a telescoping series, but we can figure out how much error we have using something called the alternating series remainder. So suppose that an alternating series satisfies the conditions of the alternating series test, aka it converges. If the series has a sum of s, so this is the exact sum, then the absolute value of Rn, so this is the remainder or the error value of the nth approximation is going to be equal to the absolute value of the actual sum minus S sub n, which is an nth partial sum. And that's going to be less than or equal to A sub n plus 1, or the nth plus 1 term of the sequence. Okay, that is a hot mess garbage dump fire of a bunch of symbol notation that if you just read it through it once, you probably don't understand right away, and I'm not expecting you to. Right? So in other words, what this means is that if an alternating series converges, you can approximate what the sum of the series is using an nth partial sum, right? And you can find that using your calculator, right? You go to like math and what option, like 0 or whatever, to find an nth partial sum. And your error has the absolute value that is no greater, right? It's got to be less than or equal to the first term that's left off of the nth partial sum. And what that means is that we can construct an interval where the actual sum of the series has to be. So that means the actual sum S is in between the nth partial sum minus the error amount and the nth partial sum plus the error amount. So let's go through 2 quick examples to show you what that means and how to use this. So this seems really confusing. It's actually very simple. It's harder to remember it than how to actually use it. So we're going to approximate the sum of the series below using the first 6 terms. Okay, so that means find the 6th partial sum. So the first thing I'm going to do is find S sub 6, right? So that's equal to the sum from 1 to 6 of this series. And now on my iPad, I don't have a TI calculator, so I'm going to use Desmos instead. Okay, right, so I'm going to actually split my screen here just so I have a little bit more to look at. Okay, so I'm going to do functions, sum from n equaling 1 to 6 of my fraction. Right, if you don't want to watch me type, go ahead and fast forward through this a little bit. We got n minus 1. And that's all over n factorial. I'm going to make it a fraction. Right? So this means that, right, this is equal to 91 over 144. So that would be our approximate sum of the series. Then it says to use our result and find the error amount. So we want to find the error, which for this is going to be equal to the absolute value of r sub 6, and that has to be less than or equal to a n plus 1, in this case 7. So all I'm going to do is plug 7 in and take the absolute value. So if I plug 7 in for my sequence, right, I'm going to do fraction. The alternator doesn't matter then, so I'm going to do 1 over 7 factorial. And that gives me 1 over 5,040. So there's my error amount. S sub 6 is my approximate sum, and then it says I also want to use my results to find an interval in which S must lie. So S has to be an element of, or S has to be inside the interval from 91 over 144 minus this, and then my approximation plus my error amount. Come on, pencil, there we go. So I'm going to use Desmos as my calculator here. So if I have 91 over 144 and I subtract 1 over 40, make that a fraction, right? That has to be inside the interval from 199 over 315, which I'm also going to write it as a decimal, 0.632, and then all I'm going to have to do is change my minus sign to a plus sign. So the plus sign is 0.632 as well. Right, if I make it a fraction, I get 177 over 280, right? And if we look back at our approximation for S sub 6, right, as a decimal, right, it's 0.6319, right? So that fits right in between those two values. So we can essentially say that the actual sum of this is 0.632 because they're the same decimal value if you round them to 3 decimal places. Okay, so let's look at one more problem. So another way that we can use the error for alternating series or the remainder for alternating series is we want to find approximations that are within a certain amount of error of the actual sum. So we want to approximate the sum so it has an error that's less than 0.001 or less than 1/1000. So I want, right, the absolute value of Rn, which is less than or equal to the absolute value of A sub n plus 1, I want that to be less than or equal to 0.001. So that tells me that my nth plus 1 term, right, and since it's absolute value, I'm going to actually get rid of the alternator. So this is just 1 over n plus 1 to the 4th is less than or equal to 1/1000th. Right, all I'm doing is plugging n plus 1 in for the n here. So now if I cross multiply, I get 1000 is less than or equal to n plus 1 to the 4th power. So if I take the 4th root of 1000, that's going to be less than or equal to n plus 1. So the 4th root of 1000, right, minus 1 is less than or equal to n. Now that's not super useful. I'm going to go over here to my calculator. So I have, let's see, I'm going to have to make this a little bigger just so I have more keys here. Okay. Functions, nth root. Okay, there we go. Right, 4th root of 1000, get out of there. Right, minus 1, that's about 4.623 is less than or equal to n. So remember close that out so we have more screen. So for series, we're using integers. So since 4.623 has to be less than or equal to n, right, that tells me that 5 has to be less than or equal to n. So my approximation, I'm going to use S sub 5. All right, so I'm going to actually have to bring this back up. Okay, so I'm going to use S sub 5. So I'm just going to edit this thing up here. There we go. So delete that, make it a 5, negative 1 to the n plus 1. And not n factorial, we're going to do n raised to the 4th power. And that's going to be equal to, that over there, right, to 0.948. So if we want to approximate the actual sum, if I can get this to go away, there we go. If we want to approximate the actual sum of the series to within an error of less than 0.001, we would use the approximation of 0.948.